Okay, so this is certainly a challenging question. It's question 17. The last part calls for some careful play, and it's quite a long question, so I don't think I've seen ever anything repeated like this before, so let's keep our fingers crossed. So let's dive into it. So it describes the profile of a beach, which is this profile. It tells you that the equation of this is y equals 0.02x squared. And it talks about y and x and heights of water. Okay, so let's go into C and zoom into this w. So the x coordinate here is 1, and it wants the horizontal component of the velocity of w. So horizontal component sounds like dx by dt, right? That already gives you a clue that it's probably chain rule, maybe, because look, I can get dy by dx from this equation. So all I need is something to do with dy by dt, and look, it tells you right there, doesn't it? The water rises at a rate of 0.2. Notice the units meters per hour, so we're dealing with meters and hours. And so we do have that extra piece of information. We've got dy by dt equals 0.2. Let's go down the bottom now and put it all together based on our information there. We've got just get rid of this guy here, let's put it up a bit. We've got dy by dx equals dy by dt, just good old chain rule, times dt by dx. Let's go ahead and sub in. Dy by dx, well, from this top bit here, it's 0.04x, a simple derivative. So this is 0.04x. Dy by dt is 0.2, and dt by dx is here. Now remember, we can kind of treat this guy as a fraction. When you get to university, your university professors will tell you that was naughty, but it's okay at our level. So I think we've got dx by dt, if we cross divide, is 0.2 divided by 0.04x. But we're subbing in x equals 1, right? Because that was the initial, well, the information it gave us for the water, right, was here. And so when we sub in, I think we get a nice clean answer. That was 0.2, my bad, over 0.04, and that is indeed 5 meters per hour. So the rate of change of speed is 5 meters per hour in the horizontal direction. Now, we're not going to finish there because there's actually an extra little something we need for part B2. And can you see here? This is a differential equation, right? Connecting x with t. So if we integrate that, we will get an equation connecting time, the time that the water's rising, with the horizontal distance that the tide reaches. So let's go and just do a little bit of work on this. I'm going to copy this. I'm going to paste it onto the next page. And we're just going to work on this. Even though we should be going to B part 1, we're going to have to come back to this anyway to finish off. So can you see dx by dt on the left? So we could directly integrate if this side was in terms of t, but it's not. So we've got to separate the variables. So let's go and do that. 0.04 dx, cross multiply 0.2 dt, integrate both sides. And we've got 0.04, oh, my bad, look, there's an x here. So I didn't bring up the x as well, and dx. So 0.04x squared over 2 equals 0.2t. There's always a plus c, but I think the question told us a bit of extra information. Look, at t equals 0, we've got an x coordinate of 0 there, right? So let's go back here, and let's not mess around too much. Yeah, look, if t equals 0, then x is 0, and you can see that c would be 0, right? So this equation is actually 0.04 x squared over 2 equals 0.2t. And when all's said and done, you have got x squared equals 0.2t divided by 0.02, right, because the 2 and the 0.04 here. So x squared equals to 10t. Now that's going to be quite important. T equals x squared divided by 10. We'll come back to this for B part 2. Now then, B part 1. So let's have a little look here. This tells us that the snail is at a particular position, and it says it's at 1, 0.02 at time t equals 0. So the water is here at time t equals 0, the snail is here. Okay? And so it's obviously a snail against the water kind of competition. And let's have a look, see if we can unpack this. It tells us that the speed of the snail, which is kind of velocity, right? There's the speed here. Now speed is tangential, so it says it's in the direction along the curve. So on this picture here, the speed of 1 here is at an angle of theta. Let me just make that a little bit thinner. So this is an angle of theta here with the slope, and that's what it's always doing. And further up, right, obviously there's an increasing angle. But this vector here is always 1. So obviously the corresponding x and y vectors of speed change. So let's keep thinking about that as we move on to B part 1. So B part 1, I've transferred the diagram. And let me just get my, there we go, pen back to normal. Can you see the red and the blue horizontal and vertical components? So this would be the rate of, the rate of change of y with respect to t. And this would be dx by dt for the snail, right? Not the water, dx by dt, okay? So that's important that we have those set aside there. But actually, if we just move those away now, let's go and actually work out the physical lengths of the blue vector and the red vector. Okay, so these are resolving the velocity, which is 1 in this direction, into horizontal and vertical components. Right? I think you'll find that it's very easy to see that this is 1 times by sine theta, and this is 1 times by cos theta, right? And get rid of the 1. From here, if that was a different speed, then obviously that would transfer across. So can you see that dx by dt equals to cos theta? Let me make it the same colour. And dy by dt, equals to sine theta. Great. But what is theta? Well, here's the big reveal, because we know that the gradient of the slope dy by dx was 0.04x. Now it turns out that the gradient of the slope is identical to tangent of theta. Now if you think about this, tan of theta is opposite divided by adjacent, because look, sine theta divided by cos theta, right? So this is the key piece. Now let's rearrange for theta. So theta equals arctan of 0.04x. And so now can you see dx by dt is cos of theta, but theta is arctan of 0.04x. And we do the same for theta here, is arctan of 0.04x. Okay, so can you see the craziness that is this question? And down below I've prepared the final piece, which is Euler's method. So here I've got the row headers. Here's txy, dx by dt, dy by dt. Initially, the location of the snail is here. And look, we have to put this in here and this in here. and then you've got to make the formulas work right. This dx by dt references this number here, so you have to relative cell reference, and this dy by dt references this cell here, and of course the next x cell references the cell above plus the dx by dt times by the step size. I made the step size 0.1, which seemed to make sense, but you have to drag down a heck of a long way to get to 9.47 meters in the x. I managed to get to 10.04, right, because the question says we have to get to 10, 2 for the snail. That's the x and y. So for the x, we're trying to head to 10, and for the y, we're trying to get to 2 above the ground. And you can see my results are here. I definitely got to 10 meters for the x at 9.3 seconds, but that gave me a 1.999. So pretty much 9.3. Remember, this is an approximation. So 9.3 seconds or 9.4 seconds. Okay, final piece. It says, this last bit, it says, hence show that the snail reaches the point 10.2 before the water does. Right, so now we're going to go back to that water piece here, look, and we've got a formula. Here is the time taken for the water to travel a certain distance. So can you see that the time taken for the water to reach an x coordinate of 10 is actually 10 seconds. So the water reaches an x coordinate of 10 meters. Oh, not 10 seconds, my bad. This is 10 hours, right? Whereas we know from our Euler's method, the water will reach, the snail will reach the 10 meters either here or here, and that is definitely before the 10 hours that the water takes. So that's really, really naughty. I think the alternative way of doing this is a formula that you don't actually know, okay? The formula is for arc length. So if you could work out the length of this arc, curve length, sorry, from here to here, right? So if we work out this distance, well, we know we're travelling at 1 metre per hour, so if we could work out this distance, then super simple. In fact, there is a formula. We integrate from the x of 1 to x of 10, and it's a square root of 1 plus, in brackets, dy by dx all squared dx. And it just goes on our calculator, where dy by dx here is the 0.04x from the equation of the curve on the beach itself. But this formula isn't taught on the course, and it's not in the formula book, so I'm not sure how you would magically use this formula, right? So I think this is a tough question. I've never seen one like it since. I wouldn't worry too much about it.